Okay, so I'm going to give you until 5 p.m. today to do that. Homework 2.4 is currently being graded, and I still have a couple outstanding assignments on 2.3 I need to grade. I'm just going to try and knock it out between now and Wednesday. I do want to mention something about homework 2.3 and some grade corrections I did recently. And with that, I'm going to tell you a little bit of a story so you kind of understand my philosophy on this. When I was in graduate school, I had a course called Experimental Stress Analysis, and it was all about whenever you're doing laboratory experiments and trying to measure stresses and strains to do proof of concept work. I mean, it would be a great class for anybody in here, civils, mechanicals, biomedicals. If you're ever interested in going to grad school, it would be a great class to have. But it was one of those classes where there was a midterm and a final, and that's it. Okay, midterm, 2 problems. Would you like to do that in here? Okay, yeah, that's what I thought. So the midterm was worth 20 points. Like, it was graded out of 20 points. And I did the midterm, and I got my grade back, and there were 5 points taken off. That was a big deal, right? Just think about the numbers. And also, I want you to keep that number in your head, 5 points. Okay? So the reason that 5 points got taken off, and it wasn't just me, it was like half the class that got 5 points taken off. And I won't get into the specifics of the math, but there was an analytical technique that I used and a couple of others used because the conditions of the problem, we thought that was the correct way of doing it. And the professor seemed to think, no, you didn't really need to go through that. And we spent a good little while debating it with the professor. And there was something that one of us said, I don't remember, but it sort of clicked with him, and he went, oh, you're right. You're right. That's a good point. I'll correct your tests. So we all gave the professor our tests back, and he gave us back 4 points. I went, oh, okay. I will remember that. Really? 4 points? My point about the story is this. Whenever I developed my teaching philosophy, I said I'm going to collect a list of all the stuff that university professors did that used to tick me off when I was in college. So I'm not going to do that. I have TAs for the class, and they grade a lot of the homework. I had a student email me about some questions regarding the grade on homework 2.3, and he said, I'm not really worried about the grade, but I didn't really understand why I got the deduction I got. And I went through the grade, and it was a reasonable question. I know why the TA made the deduction, and I'm not questioning their judgment. I thought it was fair given the conditions of the assignment. But if I was in their boat, I probably wouldn't have made the deduction, but I would have made the comment. And so what I did is I said, you know what? It's a fair question. I'm going to give you those points back. And in fact, I went through homework 2.3, and I found a few students that were in a similar boat, and I said, I'm going to give you your points back. Now, I don't micromanage my TAs. They're grown-ups. They're smart folks. They know what they're doing. But one of the things I do want to say is that even though I might not have made the deductions, they did have some pretty good points. I mean, one of the conditions of a lot of the comments were that sometimes, I don't want you to make the problems harder than they really need to be. Like, there was a resultant on that problem where the answer that I reported in the solution was just 86 degrees deflected downward from the horizontal. And a lot of people added like 180 to that. And the TA said, well, you didn't really need to do that. And I agree that you didn't really need to do that. They took off points I probably wouldn't have. But I guess my point is, if you think that there's like a calculation error or there was something taken off that shouldn't have been, don't be afraid to ask. I mean, we're human beings. The last thing I'm going to do is give you 4 points back instead of 5. I won't do that to you. Now, I mean, if you really did make a mistake and it's like, well, I think I should have gotten 8.75 instead of 8.7, like, come on. But the point is, like, don't hesitate. I mean, that student who asked that question, not only did they get their points back, but there was probably about 10 of you that got a bump on 2.3 as a result. So, and I won't go back and regrade and go, oh, you got a 9 out of 10, but you should have gotten a 4 out of 10, so I'm going to give you the 4 out of 10. I won't do that. So I'm not that mean, I don't think. That was a joke. All right. I'm going to extend the homework 2.5 deadline to 5 p.m. today to go through the hints that we talked about. And then I'm still assigning homework 2.6 that'll be due Wednesday. Okay, today what we're doing is we're entering the third dimension. Now before we do that, just want to make sure that we're all crystal clear on everything about the second dimension. We know that, the equation of static equilibrium is that the sum of the forces must be 0. And so when we're talking about 2D, we're basically saying that we have two equations and two unknowns for the most part, because we have the sum of the forces in the x direction equal to 0, and the sum of the forces in the y direction must equal 0. And don't forget this. This is probably the other thing to keep in mind, is that whenever you're given a mass, you need to convert that to weight, because weight is a force. Our equations of equilibrium are equations of condition of forces, not masses. Okay. Entering the third dimension. You'd think that doing problems in 3D would be harder. They're really not. All we're doing is making the problems just a little bit longer. That's all we're doing. So first off, we're going to be incorporating not just IJ notation, but we're going to be incorporating IJK notation. So K is going to be the unit vector that goes along the positive direction along the z-axis. Okay? Now, what we can do is just like vectors in 2D, we can express vectors in 3 dimensions using their rectangular components. So a little bit times I plus a little bit times j plus a little bit times k. In terms of drawing your coordinate systems, there's a technique called the right-hand rule. If you're ever trying to figure out which way your axes need to point, and I'll actually show you that today in our example. Most of the times in the problems that we do in here, I'm going to give you the coordinate system just so that we're all doing the problem according to the same convention. In real life, that isn't going to happen, but that's just so that we're all not doing the problem 6 different ways and all doing it correctly, but now it makes it a nightmare to grade. So the right-hand rule states that what you do is you take your right hand, you face your fingers towards the x-axis, and you curl them towards the y-axis, and whichever way your thumb points, that's the z-axis. Okay? So the idea is that, like, this would be the x-axis, this would be the y-axis, and the z-axis would point out of the screen. Now, obviously, I can't draw an arrow on a slide going like that, so that's kind of like the isometric view. Does that make sense? Okay. Now, I want to take a little bit of time and focus on this slide, because what this slide is doing is it's trying to show you that there's not a lot of difference between 2D and 3D, okay? The way that we go about it, a lot of the base calculations that we've been doing are all the same, okay? For example, vector description, a little bit times I plus a little bit times j. It's just the same thing here, just another component added on top to it. What about the magnitude of a vector? If I give you a vector in IJ format and I say, what's the magnitude? How long is it? Your first response is Pythagorean theorem. Well, can we do the same thing in 3D? Yes. How do we determine the magnitude of a vector in 3D? Just the x component squared plus the y component squared plus the z component squared. Square root of the whole thing. That's how we determine the magnitude of a vector in 3D. What about vector addition? Is it any different? No. Same idea. Just add up the x components, add up the y components, add up the z components. What about equations of equilibrium? No big mystery there. We have 2 here, 3 here. Not really much different. The only thing that's a little unique is the orientation vectors, how we do that in 3D, but it's pretty systematic. It's actually pretty straightforward. But I got to hold off on that because I have to take a little bit of a detour and talk to you about unit vectors, okay? But any questions on this so far? Okay. Now I want to go back to the definition of a unit vector, because when we first started to talk about I, J, and K, like let's go back. What are I, J, and K? They are unit vectors. They are our essential unit vectors because they are of a magnitude of 1, and the reason why we say that there are essential vectors is because they point along the axes of the coordinate system. So the I vector is a magnitude of 1 oriented along the x-axis. And same thing with j and k, etc. Well, if you recall, just back to our base definition of a vector contains a magnitude and a direction. What I want you to do is imagine that if I have some vector, what I could do is factor out the magnitude. So I have some vector here of magnitude f and some orientation, it doesn't matter. If I factored out that magnitude, the orientation would remain, but I'd have the magnitude out here of f. That means that whatever's in this box here would have the same orientation, but a magnitude of 1. What's inside this box here would be a unit vector. So what we'll do here in 3 dimensions is this will be how we describe vectors in 3D. So what we'll do is we'll say that the unit, or the force vector, I'm just using f for force vector, the force vector will be some magnitude, we'll call it f, times a unit vector, and this little weird letter here is the Greek letter lambda. And so what we'll try and do is define lambda as the unit vector in 3D. Okay? The hardest part is determining that, but we do have a little bit of a trick that we can use, and it involves using the dimensions and the distances that are present in the problem. Okay? Let me show you how that works. So if you have some vector out in space, okay, so let's say you have some force vector out in space, what you've got to do is you've got to come up with a definition for that vector, an IJK definition for that vector. That's kind of tough because how do I determine the orientation? Well, what I can do is if I know the vector is going along this line, line MN, what I can do is define a vector for MN. What I do is I take the coordinates of this point, the x, y, and z coordinates of this point, subtracted from the x, y, and z coordinates of this point, and boom, there's MN. Now, the problem is that's not a unit vector, okay? That's not a unit vector because that's going to be, you know, I don't know, 3 feet this way and 7 feet that way and 4 feet up. That's not a unit vector. Those are distances. But what if I take that distance vector and I divide it by its own length? So I take this MN vector and divide it by the length of MN. What do I get? A unit vector. And so then if I take that unit vector, multiply it by the magnitude of the force, boom, we're in business. And that's going to be the focus of what we do today in our in-class example. The only thing that I have to go back to, that whole more on this later, is the orientation. In 3D, what we do is this. We have our unit vector right here. We take our unit vector and we recognize that these unit components here are just the cosines along the axis in question. So, for example, this lambda x, if here's my vector and the vector has a length of 1, lambda x is just this length here. It's just this projection here. And why am I doing cosine? Well, cosine is adjacent over hypotenuse. And so if the length is 1, then this length is just the cosine. So if you want to find the orientation of your vector, it's actually really easy. All you have to do is take your unit vector and take the inverse cosines of these numbers. It's really straightforward. And what that'll tell you is the angle from each of these axes. So if you get theta x is 20 degrees, and this is 40 degrees, and this is 50 degrees, your vector is 20 degrees off the x-axis, 40 degrees off the y, and 50 degrees off the z. It's actually really, really straightforward. Concepts and ideas make sense. Don't worry, we're going to exercise them here in a bit. Last thing I'm going to do is say, all right, figure it out. Have a good day. I could do that, but that would just be mean. Again, I'm not a mean guy. I don't think. Any questions? All right. So we have here a wall that's held in place by some cables, and ultimately what we're going to be doing is adding up forces. We're not doing an equation of equilibrium yet, but what I want to do is I want to look at this point here, A. Okay? This point here, A, has a cable here, and a cable here. Now they're both yanking on A, right? The tension in this cable right here is 840 pounds, and the tension in this cable right here is 1,200 pounds. And what I want to do is, okay, I got 840 pounds yanking this way, and 1,200 pounds yanking this way. What's the resultant? And remember, that's like one of the first problems that we tried to address here, is if I have a point, and I have a bunch of forces added onto that point, I can idealize that as a single force, the resultant. That's going to be our first task here. So we're going to determine the magnitude and direction of the resultant of the two forces on point A. Sound good? All right. Don't worry, I've got my notebook here, and it's got everything. Did I? That would help. Come on. Okay. So here's our problem, and I sort of cheated a little bit here because I copied this image twice. So what I'll do is I'm going to scroll down here a little bit, and I copied this image here twice because what I want to do is I want to first off define these distance vectors. Okay? So the way that we're going to do this in 3 dimensions is whenever you have a force vector in 3D, the easiest thing to do is to define the distance vector along which that force is applied. Once you have that distance vector, you can take the distance vector, convert it into a unit vector, take the unit vector, multiply it by the magnitude. Don't worry, I will walk you through it. Now, in order to do these distance vectors, we have to have a coordinate system that we all agree upon, okay? So here's what I'm going to do. I'm going to say, and it doesn't really matter where I place this coordinate system, but I'm going to sort of place it right here. Like we'll say that little point right there, that's the origin. I don't know if you can see that little point right there. That's going to be the origin. And so what we'll do is we'll say that that's the x-axis. We'll say that's the y-axis. And then your right-hand rule, x, y, z is pointing down the wall. So there's my distance vector, or sorry, there's my coordinate system. What we're going to try and do is we're going to try and define 2 distance vectors, AB and AC. Okay? And what we're going to do is we're going to say this is something times I plus something times J plus something times our new vector K. Now, if you're following along with me, I mean, you could try and draw this image if you want. I probably wouldn't recommend it just because of the amount of time it would take. But what I want is for you to sort of have this distance vector template set up, because what we're going to do is I'm going to do the first one, then I'm going to have you all do the second one for me. Okay? All right, do you have this part set up? Okay. All right. Let me ask you a question. Okay, so what we're going to do is we're going to define these distance vectors from A to B. Now, what we could do is we could do the way I said in the slides, and the way that I said in the slides would work. We can find the coordinates of B and the coordinates of A, take the coordinates of B minus the coordinates of A. We can do that. I think the easiest way to do this is to just sort of look at the image and see which way you're going and how far along each axis to get to the places that you want to go. So everybody watch with me up here, okay? We're going to go from A to B. So this is the x-axis. We're going to do x, y, and z. Let's do x first. So that's the x-axis. To go from A to B, see how I'm going 16 feet? Now, is that positive or negative? Negative. So this is going to be negative 16 feet. Okay? Now for the y, okay? Y is up the wall. That's, up and down. So from A to B, I'm going up. And I'm going up a distance of 8 feet. For Z, that's down the wall, and I'm going positive along the wall a distance of 11 feet. That is AB. That's your distance vector. Did that make sense? Now, if that made sense, I'm going to call on some volunteers. For vector AC, what goes here? Somebody tell me this one. Negative 16, that is correct. What about this one right here? 8, that is correct. What about this one right here? Negative 16, right? The wall is 27 feet long. From here to here is 11, here to here is 16, but you're going the opposite direction. So this is that's that. I guarantee you that is the hardest part of this problem. If you've got that, everything we're about to do, while long, is cookie cutter. It's plug and chug. It's a process. Okay? Any questions on that? Yes, sir.
Did the origin have to be at the end of the wall, or could we have made the origin a stake?
We could have. That's a great question. The answer is it could have been anywhere. Okay? Because here's the thing. What we're trying to do is figure out how far it is to go from one point to another. Okay? So here's the best way of answering that. How far is it from here to Morgantown? You don't have to be exact. Just give me something. The answer makes sense. You can measure it in hours or miles. Doesn't matter. About 3 hours. Does it matter if I ask you that question here or if I ask you that question in Miami?
Yep.
No, I'm saying how far is it from Huntington to Morgantown? That distance is always 3 hours or however many miles. It doesn't matter if that question gets asked in Huntington or Miami because that distance is still absolute. The origin, where you place the origin doesn't really matter. Because you're still taking the coordinates of this point minus the coordinates of this point. And because those coordinates are both measured from the same origin, it's fine. Does that make sense? Does that make sense to everybody else? I didn't ask that question in the most clear fashion initially, so my apologies. I meant from Huntington to Morgantown, not from Miami to Morgantown. Yeah. That would be a drive. Any questions? This is good stuff. Okay, so what we're going to do is, again, this follows a clockwork process. The first thing that we're going to do is compute unit vectors. So, does anybody remember, and I know I just showed you, so I might have shown you a bunch of formulas that might have glossed over. But if I give you a random vector, how do I convert it into a unit vector? What do I do? I take that vector and divide it by what? But divide it by its own magnitude. So I take a vector and divide it by its magnitude. So here's how we're going to do this. So let's take vector AB. How do we determine the magnitude of vector AB? Let me scroll up a little bit so we can read vector AB. All right? So how do we do that? We use the Pythagorean theorem. We just use all three terms. So 16 feet, that's negative, squared, plus 8 feet, squared, plus 11 feet, squared, and we take the square root. What do we get? Which, by the way, the values in this problem were set up to where they're all pretty answers at the end. $21. Do I have a second on that? Yeah. So therefore, the unit vector in that direction is just it's just that, right? Now, if you wanted to express that in decimals, you could, but what I'm going to do, and there's a reason I'm going to do this, I'm going to rewrite this as follows. I'm going to say it's negative 16 over 21 times I plus 8 over 21 times J plus 11 over 21 times K. Now, why did I do that? What changed from here to here? I'm sure some of you are like, well, nothing changed. Well, no, something changed. I dropped the units. Now, that might seem innocuous, but that's actually sort of my whole point. By dividing it by its magnitude, not only does this vector now have a length of 1, and if you don't believe me, square this, plus square this, plus square this, take the square root, you'll get 1. But by dividing it by its own magnitude, you've removed the units. All this vector now is a vector pointing in the direction of AB with a length of 1. That's all it is. And that will be very valuable here in a bit. So for AC, and I'm trying to do this in such a fashion to where you can see the vector here on the top. So if you see what I'm writing, you're like, oh, okay, I see where he's getting these values. What do we get for this magnitude? $24. Do I have a second on that?
Yeah.
All right. So 24 feet. So now, and I'm going to scroll down a little bit because I don't want to squinch this. So now I'm doing the same thing. I'm dividing each of these by their magnitude, but I'm also going to simplify the fractions a little bit because I've got 8 over 24, which reduces to what? 1/3. And so that's 2/3, and that's 2/3. So negative 2/3 times I plus 1/3 times J plus negative 2/3 times K. And you can definitely see that this is a unit vector because 2/3 squared is 4/9. So 4/9, 4/9, and 1/9 is 9/9. That's 1. So take the square root of that, you get 1. What do you think? Everybody good so far? So here's where the magic is. Here's where the money is. So we took distance vectors. That was step 1. Step 2, we converted those to unit vectors. Now we're going to take those unit vectors and convert them into force vectors. Let me move that down a bit so it's not all squunched. And what you do for a force vector is you take the magnitude and multiply it by the unit vector. Okay, before we stop, I brought a bunch of extra cables today. My surface here looks like it's running low on power, so I brought my power cord for that very reason. There we go. Now I just have to make sure I don't kick the cable. Okay. Now, does anybody remember at the beginning of the problem, we were given the tensile force in AB and the tensile force in AC. What were those? What was AB? 840. And this one was 1200. So, is it okay if I scroll a little bit? Okay. So what we're going to do, if we want to define this tensile force in AB, what we're going to do is take that magnitude times that unit vector. So we've got 840 pounds times negative 16 over 21 times I plus 8 over 21 times J plus 11 over 21 times K. So what are we getting for this I component? Anybody tell me for that? Let's do I first, then J. I'll probably do K.
Negative 640.
Second?
Yeah.
All right, what about the J?
320.
Second? All right. And then this one, I'll go ahead and tell you, it's 440. Okay? So what we did is we took this 840-pound force that was just sort of acting that way and split it up into its X, Y, and Z components. So now we know it's negative 640 in the X direction, positive 320 in the Y, and positive 440 in the Z. So the value of that is if we do the same thing with all of our forces, we can just add them all up by adding all their components. So that's kind of the idea. All right. Let's do AC. So same concept. All right. 1,200 pounds. That's a different vector. This time it's negative 2/3 I plus 1/3 J. Is it minus? Yeah, it's minus 2/3 K. I'm writing a lot of fractions, a lot of positives and negatives. If you see me have a typo, let me know. All right, this one's pretty easy because it's 1,200 and it's thirds. So I think I can eyeball this one. I think this one's going to be negative 800, positive 400, and negative 800. So far, so good? Okay, so how do you find the resultant vector of a bunch of vectors that are expressed in ij notation, you add up their components. So we've got their components. Now we can find the resultant. I'm going to scroll down a little bit. You okay with that? So the resultant vector is found by summing just the initial vectors. And so I'm trying to write the formulas that go along with this. So sorry if I'm being silent here. I'm just trying to copy down these vectors and make sure I don't get a sign wrong. And so all I'm doing is I'm saying, okay, here's TAB, here's TAC, and I've lined it up. And again, I kind of like putting all my positives and negatives inside the parentheses so that I can just add them up directly. What's the resultant? It's just the sum, which is, okay, so if I have negative 640 and negative 800, that's what, 1440? 320 and 400 is 720. 440 and then negative 800 is negative 460, 360. Yeah. There you go. There's your resultant vector. Now, the only thing left to do is two things: the magnitude and the direction. I'm going to scroll down a bit. How do we find the magnitude of the resultant vector? There you go. Anybody have an answer on that? Now that one's not going to be pretty, so we'll probably need like 2 decimal places. I know we're getting close on time, so I'm going to try and go through it quickly. Anybody got an answer? All right. Second? All right, good. So that's one of our answers. Now we need the direction. And given our time constraints, I'm going to do this one kind of quickly. But I think you'll find it's pretty systematic. So whenever you think direction, you should think unit vector. How do I find a unit vector? How do I find the unit vector of the resultant? I take the resultant vector and I divide by its magnitude. So what I'm going to do is I'm going to take negative 1440 pounds over that times I plus that times J plus that times K. And I'm not going to make you do all that. I'll do it for you since we're running short on time. But again, all I'm doing is just taking these, dividing it by the magnitude. Now, these are going to be kind of nasty, so I'm just going to write these out. And I'll do like 4 decimal places so that you can match and see if you get the same values I get. So that's what I got when you chug this out. You can follow along with me. I think you find that's pretty straightforward. I propose that this is the unit vector in the direction of the resultant. It is also defined as the directional cosines. So if you want to find the angles from these axes, just take the inverse cosine of these numbers. So, and I'll scroll down and do that right here. So therefore, theta x is the inverse cosine of that. And if you do that, you're going to get like 150.79 degrees. And in 3D, I think it's easier to just, whatever the math tells you is the answer, just use that. That was going to be my jam. I know, we're cutting it on time, I know. All right. I know I did that very, very quickly, but I think it was pretty systematic, so I think it was pretty straightforward. Does anybody have any questions on that? All right. On Wednesday, last topic for the first exam, which is 3D equilibrium. Bring your scientific or graphing calculators. You'll need them then too. That's all I've got, everybody. I'll see you then.